What's up, everybody? Welcome back. Friday Science. Gonna have some fun today. You notice I got a new prop. All right, carried this all the way from the classroom, although it was in the back room, and we're saving it for this lesson because we are going to be talking about water, as we've been talking about fluids. I want to show you something. We're going to try some new technology. Excuse me. Ready for this? Ooh, snap! Look at that! So right underneath me, right there, boom, we've got your unit binder. So let's just kind of look at that for a sec. Going through this, we are on lesson 6. Okay, we are about halfway. Okay, and remember that we are not going to be doing the culminating task virtually, because that would require you having syringes, okay, and tubing, and it is not the time for me to be asking you to go and buy things, and so we won't be doing this. However, on last Friday at our Science Guided, we were talking about it together, and we said that maybe if we get back like mid-June, maybe we could just have some fun with this final project. So hopefully we look forward to that. Okay. All right. So we are talking about buoyancy today. Buoyancy. Okay. And we are going to play a little game called Sink or Float. All right. So in the chat, I need to hear from you. There it goes. Okay. I need to hear from you if you think something's going to sink or float. So, for example, I'm going to bring you some random objects. Okay, the light switch cover. Is this camera on? Working? Oh, it's so glitchy. Okay, the light switch cover. Let me know in the chat. Do you think it's going to sink or float? If you don't feel like writing sink or float, why don't you just write S or F? Or give me a check or an X. Or a yes or a no. Are you ready? Here we go. 3, 2, 1. It floats. It floats. All right. Let me know if you got that right. Here we go. How about some Lego? Lego. What are you determining whether it's going to sink or float? What are you using to determine this? Oh, the leg is real. There. Oh, man, that is very leggy. All right, here we go. 3, 2, 1. It's a half sink, half float. I think that goes float. That is, we can count that as a float. That is a floater. Oh, we are 2 floaters. No sink. All right. How about a syringe from your final project for this unit? Okay. Will it sink or will it float? All right. Seeing some answers. Here we go. 3, 2, 1. Another floater. Woo-wee. Kids, maybe nothing. Maybe this is magic water. Maybe nothing will sink in it. All right, here we go. I got some rubber. Okay, this is rubber. Okay. See how you twist it, bend it. Okay. Do you think this is going to sink, or do you think it's going to float? There you go. Look at it. Let me know in the chat. Sink or float? Sink or float? Predict. Observe. Here we go. Move some stuff to the other side. It's full sinking. We got a sinker. Our first sinker. It is proof that this is not magic water, that you can sink in this water. All right. How about a pipe? How about a pipe? All right, little fact. This is from a lawn chair. My lawn chair was going in the garbage. I cut it off because I needed to run some cable through it, and I no longer need to. So, do you think this pipe will sink or float? Let me ask you, why do you think it'll sink or why do you think it'll float? Okay. Here we go. I really wish my second camera was working better. There we go. The pipe in 3, 2, 1. That sang hard. That sang very hard. Okay. Now, some of you were asking about the syringe. You said it floated because I opened it all the way up. So what if I close it? Do you think that'll make a difference? Do you think it'll sink now that I've closed it? Let me know. Sink or float? Syringe. Will it sink or will it float now? There we go. Closed syringe. Okay, just to remind you that the open syringe is floating nicely on top of the water. So now we're going to try a closed syringe. Ready? 3, 2, 1. It's floating. It is floating, friends. It is floating. I'm wondering if I can lower this, even though it's pretty useless right now because it's all laggy. See if we can get anything from under. All right, here we go. Continue. We have 2 syringes, open and shut. It floated. But what if I fill the syringe with water? So let's take some water. You know what? We already proved that this floats. So let's fill it with water now. Okay, half full or half empty. Here we go. Tell me, is it going to sink or is it going to float? There we go. In 3, 2, 1. It's still floating. Ooh-wee! That's crazy. That is crazy. That's crazy. It is still floating, friends. All right, let's fill it all the way up. Hey, the syringe is full. So you know. Okay, there you go. Fill it back up. Hey, a full syringe. Do you think it's going to sink or float? Let me know. Let's blow. And 3, 2, 1. Oh! I sense a lot of people were wrong there. I think a lot of you were saying sink. I know I was saying sink. I didn't want to mess with your, but I was like, that's for sure sinking when it gets full. Wow. Okay, so syringes. That's impressive. Good to know. All right, how about this? How about a screw, a wood screw? Sink or float? Call it. There we go. 3. Lock in your answers. 2. Predictions. 1. Sank like a rock. How about an eyedropper? 3, 2, 1. Yeah, you knew that was floating. What if I fill it though? Now it's full. Ready? 3, 2, 1. Doesn't matter. Let's really, really fill this. Yeah, I can't fill it anymore. What if I drop it this way? Nope. It's gonna float. All right, you know I play guitar. What about one of my guitar picks? Shout out Long McQuaid. Here we go. 3, 2, 1. It is slowly sinking. It's a sink. Guitar pick is a sink. Okay. How about this? Similar to our syringes, I have some test tubes here. Okay. Let's just do this. Here we go. I've got a test tube that is open. 3, 2, 1. Oh, what are your predictions? Sink or float? Open test tube. 3, 2, 1. It floated until it filled with water and then it sank. So, let's do this. Empty. Put the cap on. Now, sink or float. There we go. 3, 2, 1. It's a floater. All right, let's leave the cap on with water in it. 3, 2, 1. Look, 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 look at that. I bet you thought that was sinking, didn't you? That is a half float, half sink. Wow, but the power of the float is holding it up, even if I push it down. All right, all these objects. Oh, there, I broke the surface tension. That's a flashback. And I was able to make the light cover sink. What about the Lego? Can I make it sink? No. Yeah, it just pops right back up. Syringe pops right back up. Wowzers, folks! Okay, what about a piece of wood? Piece of scrap from my hardwood floors. You ever wanted to know what my hardwood floor color was? It's that one. Not the unfinished one part. Okay, sink or float? Let me know. 3, 2, 1. Float. Now maybe some of you are thinking, oh yeah, like logs float, so that makes sense. Or maybe some of you are thinking, just wait until it gets soaking wet and then maybe it'll sink. Huh? We'll find out. What about a pencil? Pencil. Here we go. 3, 2, 1. It also floats. Okay. What about a submarine? This is here we go. This is actually a special submarine. This submarine is supposed to be cool. It was very cool the first time that Kirby and I tried it, and then after that, it failed. But I'm going to try it again here, live for you, on video, in class, and let's hope. So I am going to fill it with baking powder. Not baking soda and not baby powder. This is baking powder. So what I'm doing is there's a little inside to it. Okay? I'm filling it. Okay? So I got it full with baking powder. Wipe off the top. Good clean. I'm going to put the top on. We're ready to go. All right, now watch carefully, watch closely, get ready, get set. I really want to see if this view will work. This is still struggling. Not gonna work. All right, let's go back to our full screen camera. All right, here we go. So what I'm going to do is I'm going to put this into the water. I'm going to hold it by the top here. I'm going to shake it. Okay, and then we're going to see how it responds underwater. So let me just move some stuff out of the way. All these floaters, get out of the way. And there it goes. It's sunk. It's at the bottom, like a submarine should be. But suddenly, it arises up from the bottom of the water and rises to the top. And then it sinks. It's working. Oh, my Lanta. Kirby, it's working. Oh, it's going back up. It's going back up, folks, to the surface. It gets us some breath. And is it going to do it? Is it going to do it? Oh, no, it's tipping over and it goes down. Down it goes. How is this possible? Oh, my goodness. This is like Christmas. I can't believe it's working. Kirby and I tried this a million times and it never worked like this. Look at that. Oh my Lanta. It is going down. It is going up. It is showing you buoyancy, folks. Today we are learning about buoyancy. We're going to talk about why submarines sink and float, why fish can sink and float. And we're going to be talking about things that we're doing that are hurting fish's ability to sink and float. Super interesting. And I'm so excited it's working. Way to go, submarine. There it goes again. Oh, down he goes. Down he goes. Oh, snap. That is sick. All right, so let's jump back here and let's talk about buoyancy. Oh, man, I really want my camera to be seen. I want to see it. So let me just play with my camera for a sec. And then we'll move this laptop, the PowerPoint screen down. All right, here we go. We're talking about buoyancy, okay? So you're going to be taking notes here. Let me just scroll ahead. We just finished the density slides. Okay, we talked about discovering density. These should all be done. Okay, we did density calculations with the triangle. Okay, these should all be done. Done. Okay. So right after this slide in your unit binder, we're at buoyancy, lesson 6. Okay. Your slide says that density and buoyancy have many applications in our world. We're going to watch some video clips. But before we get to the video clips, go ahead and take some lesson notes. Okay? So write this down. Buoyancy is the upward force. Okay? The upward force acting on an object in a fluid. Okay? So what you're seeing here is that this Lego has an upward force holding it from sinking. Okay? So that's buoyancy, and that submarine is still going. That is sad. Still down and up. That is awesome. Okay? So, all objects that are in fluids are subject to 2 forces. Very important here. Okay? All objects in fluids are subject to buoyancy and to gravity. Buoyancy and gravity. You know what? Make sure you got that down. Put that down. That is so important. All objects in fluid are subject to buoyancy, the upward force, and gravity. What do we know about gravity? The downward force. Okay, this is a bit of a tug of war, an opposite tug of war. Okay? When an object goes in water, so when we were playing sink or float, what determines if it's going to sink or float is the difference between which force wins this tug of war. Okay? If you put an object in and gravity acts stronger, then it will sink. Hence all these things at the bottom. But if buoyancy acts stronger, then all of these things at the top of the water. Okay? Now, this awesome submarine that we're watching go up and down is exchanging between the 2 buoyant forces. And we're going to see how that actually happens. Okay? So, here's an awesome diagram that I spent way too much time making. Okay? If something floats, okay, here you're going to see that gravity, and this arrow is a bigger arrow, so greater gravity, remember vector, okay, and here is a smaller gravity, okay, less gravity is affecting this, okay, and on the other end, what's the second force? Let me know in the chat, what's the second force that's coming from underneath from the water? I really hope everybody's saying it. Blow up the chat. Buoyancy. Okay? So, we always say that anything in a fluid has two forces acting on it, gravity and buoyancy. Okay, so in this example, this item is floating. Okay, that's floating because the buoyancy force is greater than the gravity. So in this tug of war between gravity and buoyancy, buoyancy is winning, and so it floats. Over here, gravity has a greater force. It's winning the tug of war. Okay? So this object will sink. So that text there is just what I just said. So the red one says when the buoyant force is greater than the force of gravity, the object will float. And the other one says, the yellow says when the buoyant force is less than the force of gravity, the object will sink. Okay? All right. Here we're going to talk about Archimedes Principle. Okay? Now this is going to come up. Archimedes. It's Archimedes. Okay? And you're going to get used to this graphic right here. And here's what Archimedes says. Okay? Archimedes states that the buoyant force on an object is equal to the mass of the water that the object displaces. Huh? All right. So we need to explain this a little bit better. Okay. When I put something in the water, okay, let's go full screen here. Okay, when I put something in the water, and I'm forcing this into the water level will actually go up. Okay? And we talked about this water level going up. Do you remember we talked about that earlier? What would we call that? Remember displacement, right? Displacing water, putting aside. Now, I've gone ahead and brought a bigger object, so hopefully we can displace this water a little bit more. So what I want to do is write on this. I don't know if you can see that. Okay, so this is our water level. Okay, and then let's put something brought to you by COVID. All right, let's put this in the water and watch as our water level rises. Now, we talked about this already. And I got it up to there. Okay? So if you're able to look closely, I was able to displace, remember, this is a pretty big tank, right? So if this was a smaller, like we did with our, okay, here we go. So if I was to displace in a smaller, you could really see a dramatic raise. And you notice that when I put this in, it displaced that water, so it actually left the beaker. and I put it in, it displaces the water because the water needs somewhere to go. Okay? So Archimedes states that the buoyant force on an object is equal to the mass of the water that the object displaces. So what the heck does that mean? Okay? Stick with me here. Right now, I am not collecting the water that is escaping. Okay? If I was to have a second container in which I could capture all of this water that is coming out when I displace it, Archimedes says that I could weigh the mass of that water that was displaced to actually calculate the buoyant force. Now, probably you're sitting there and you're very confused, and that's okay because this is just me introducing a topic. You've never heard of Archimedes. We're just kind of touching into buoyancy. You've heard that word before, but nothing like this before. Okay, so coming back to the slide. Okay, Archimedes states that the buoyant force on an object is equal to the mass. So, see if I can get this going again. Okay, so watch this yellow thing. As this yellow weight goes in, okay, things I want you to notice. The water level here is right at this lip. So no matter what you put in, it's going to displace water and it's going to spill over into our reservoir. That's going to collect all that spillover water, the displaced water. Okay, so put the weight in, water gets pushed out, displaced, and we're going to stop. It says the buoyant force on the metal equals the weight. So remember, as it goes in, buoyancy is pushing back up. All right, here we go. Buoyant force on metal equals the weight of displaced fluid. So all of this water was displaced when this weight went into the water. What does that mean? Okay, so when we put a 5 kilogram object, so 5 kilograms, okay, when we put that into the water, it displaces 2 kilograms of water. So here's step one. We put 5 kilograms of 5 kilogram weight into the water. Now notice this is the weigh scale. This is the spring scale, just like we've been using all year. Okay? The spring scale is reading 5 kilograms. But when you put something in the water starts to bear some of the weight. So you'll notice that underwater, this weight now only weighs 3 kilograms. So what's holding that weight up? It's the buoyancy. Okay? So the buoyancy is actually lifting 2 kilograms of the 5 kilogram weight. Well, let's check over here at the water that spilled over. This is the displaced water. And if you were to put this onto a weigh scale, as they did, the weight of the water that was displaced happens to be 2 kilograms. Are you following here? Okay? The weight is 5 kilograms. The buoyant force lifts 2 of those kilograms. So now it only weighs 3 kilograms. You have to total 5, because that's how much it weighs. And when we put in the water, water spilt over, and the remaining water, or the displaced water, weighs 2 kilograms. 2 kilograms is the force, the buoyancy force. Okay? This is a new concept, but that should kind of blow your mind just a little bit if you're getting it, you're understanding it, and then you'll be like, whoa, that's kind of cool. Okay? So a boat is filled with air, so it's less dense than the water. We talked about density. Okay? The boat displaces water equal to its weight, so it floats. All right, so the boat's mass is 1,000 kilograms. It displaces water. So when you put a boat into the water level technically rises. Now, boats are in such a large body of water, you're not going to not even close to microscopically see that body of water raise. Okay? But when a boat goes into the water, it displaces the water. The water has to go somewhere because all that air in the boat, there we go, all the air that's inside of this boat, okay, has to push the water somewhere. So in my example, you can see it going up just a little bit past the water level. And with the Lysol wipes, it came all the way up to that black line. Okay? So boats displace the water in a way that it'll balance and it'll float. Okay, so here's some new terms for you. Added to the word wall: buoyancy, buoyant force, Archimedes Principle. Okay, some key terms here. All right, so let's get to the fun of the lesson. Now, we're going to watch some videos. Okay? And I'm going to post these videos under the live lesson link that you can watch on your own. Okay? But what I'm going to do is, as if I was in class showing them, I'm going to pause it, comment on it, and you're going to take notes. So, going to this slide now. Okay? That slide. Okay? Density and buoyancy have many applications. Watch these in the following videos. All right, here we go. So you're on this slide right now. Buoyancy basics. How do ships float? There we go. Crank the tunes.
How can a ship that weighs a massive amount float in water while small things like pebbles sink? When a ship is in the ocean, gravity is a constant downward force on the ship. But the water that the ship is in has a constant upward force on the ship called buoyant force.
This is what we discussed.
Archimedes' principle is that the buoyant force of a fluid is equal to the weight of the displaced liquid. A ship will float as long as it weighs less than the amount of water the hull can displace.
I meant to stop you and back you up and remind you that you're taking notes as you watch this. So this question, first question says, what are the two forces that act on a ship in the ocean? What are they? Okay, so in that orange square, rectangle, you should be writing gravity, and in the blue square, you're writing buoyancy or buoyant force. Okay? At this point, I think you should be able to state Archimedes' principle. Okay? So now let's listen for how does the size of a boat's hull impact its ability to float.
Called buoyant force. The buoyant force of a fluid is equal to the weight of the displaced liquid. A ship will float as long as it weighs less than the amount of water the hull can displace. Container ships that transport heavy loads use especially long and wide hull construction to increase the maximum amount of buoyant force a ship can withstand without sinking. If a ship's load is too heavy, it will sink.
Whoopsies! Okay, so looking at question 3, how does the size of a boat's hull impact? Well, the size of the hull is important because the bigger the hull, the greater the more water it displaces. The more water it displaces, the more chances for the more amount of buoyant force that can be applied to that ship's hull. Okay, so you don't really want to be carrying a heavy load in a tiny hull boat because it doesn't displace enough water to have enough space for gravity or for buoyancy to fight gravity. Okay? Most of the boats that you see would be what? The size of one of these containers. Okay? But by making a massive hull, buoyancy has a greater ability to act and lift and carry more weight of this ship. Okay? Now I'm not going to pause here and let you take some notes because you can come back in this video. All right? Otherwise these videos end up being really long and then I get trouble. People are like, "MrStav, video's too long." Okay, so we'll move on. So this is going to require some work after the lesson. I'm not going to be giving you time now. You can go back and do these. So the next one we're going to look at are airships, like blimps, and we're going to look at balloons. Okay? So the questions you're listening for are, why do helium balloons float? What is the force acting on the balloon? And then we're going to look at an experiment, and we're going to say, why does the hanging balloon appear to move backward? And we'll read the next ones as we get a little bit further in. If you zoom right in, you'll see a little bit.ly. All right, so this will take you directly to the actual video on YouTube. Okay, or you can go to MrStav.ca/science, and I'll put the link there as well. Okay, so here we go.
Hi there. How's it hanging? Or should I say, how's it floating? Speaking of floating,
Good one.
why does this balloon float?
Helium balloons float because the density of helium is less than the density of air.
Because they're lighter than air.
Because helium is less dense than air.
I'm hearing a trend in the answer. But there's one more question. What exactly is the force acting on the balloon?
I actually don't know.
That's the
I'm not sure. The buoyancy force.
Bingo! The buoyancy force. The same force responsible for keeping boats from sinking and duckies from drowning. But how exactly does buoyancy cause helium balloons to move upward? Let's head over to the physics department at MIT to do a little experimentation to find out. Here we are with the Technical Services Group at MIT. They picked out a demo that's going to help us find the answer to our buoyancy question. Now, check in your brain, because this is what you need to know about the setup, and then guess what? You can try it at home. This is Dan, a gentleman of TSG. He has placed two balloons in a box. One balloon is filled with air and is hanging from the top of the box.
Okay? Very important that you understand this experiment. This green balloon is full of air. Okay, just air. It's like, right? You can blow it up, tie it up, and then you've hung it to the top of this box. Okay? The red balloon is filled with helium. So this is tied to the top, and because it's a helium balloon, they float, it's tied to the bottom of the box.
The other is filled with helium and is taped to the bottom of the box. The box is loosely closed and therefore filled with air.
Okay, that's an important fact. It is a closed off box. It is sealed. Okay, so it is filled with air. It's not vacuum compressed or anything, it's just air.
Is going to give the box a push, and we'll see which way the balloons will move inside the box. Will they move backwards or forwards? Let's see. Did you see it? Watch again.
Oh my goodness, I ruined it.
From the top of the box. Dennis can move backward, and we'll see which way the balloons will move inside the box. Will they move backwards or forwards? Let's see. See it? Watch again. The balloon filled with air hangs back, while the balloon filled with helium appears to spring forward. What? How will we ever explain this? With science. Let's take a look back at the setup. The helium balloon moved forward while the air balloon fell back. First, let's explain the hanging balloon's behavior. It hangs back just as you do when you're sitting in a car accelerating forward. You feel like you're pushed back in your seat because really your body wants to stay where it was. Similarly, the hanging balloon.
So you know that feeling, right? When you're sitting in a car, and then they go, mm. So what she's saying is, you're actually not going anywhere. You're staying put, but the car is moving forward. So your seat is actually moving forward, which makes you feel like you're being pushed back in the seat. Right? So you're here, and then your seat goes, bam. So you feel like you're getting pushed back.
To stay in place as the box moves forward, so it appears to fall backwards in the box.
So listen to her words carefully. It appears to fall back. And in actual fact, the box is the one moving forward. That balloon is actually staying put. It's staying where it is.
Now for the helium balloon. Maybe the closed box makes the difference. Let's take a closer look at the air particles in the box. Before the push, the air is equally distributed and the pressure caused by air particles bumping into each other is the same throughout the box. As the box is pushed forward, the air particles, just like the air-filled balloon, are left behind.
Okay, so understand that. This is like particle theory. All these particles, they're moving around. Okay, but they don't get the memo that, oh, the box is moving, we should move too. They just continue moving as they were going to normally, and then the box moves on them. Okay, so then how does this affect the helium?
They're at the back of the box. Now we have a pressure imbalance. There is higher pressure and more air particles bumping into each other at the back of the box than at the front. Aha! There are more air molecules bumping into the balloon from the back than from the front. So the high pressure in the back must push the helium balloon forward, and that's the motion we see. Now we can look at why balloons float up into the sky. When a balloon rises up in the
Okay, so she's taking this concept, she's turning it, and talking about why helium balloons float. So looking in your notes, that's question one. Why do helium balloons float?
atmosphere, it must also be moving away from high pressure air to low pressure air. That sounds right. Up at high altitudes, the air is much thinner.
Okay, less air particles higher in the sky than where we are. Okay, that's why if you go mountain climbing, it's actually harder to breathe.
It's at a low pressure than at sea level. This is why hikers often bring oxygen to the top of Mount Everest, because the air at the summit is so thin. The air pressure difference is drastic from sea level to the summit of Mount Everest. But what about along the length of a balloon? Sense it or not, the difference is there. The slight minuscule change in pressure from below the balloon to above it is enough to
Notice the difference in the color yellow? So it's small, but it's there.
overcome the downward force of gravity, cause a net upward push on the balloon, and voila! We have found our missing force.
And there you have it. Buoyancy can be neutral and keep things in one place, like our floating canoe and our duck. But it can also be responsible for the acceleration or overwhelming push on one side of an object, causing it to move.
Okay. So there's 4 questions there. And you can go back and you can watch these videos as much as you want. You can pause them, go back, or you can watch this video with me at my commentary as much as less as you want. Okay, and fill in those questions. 1, 2, 3, 4. Okay. And let's go to this one. Oh, snap. Here we go. Let's talk about submarines. Let me get the submarine here. This guy, my hero, showed up big during lesson time. He did his thing. Oh, man. All right, let's watch this video.
They can reach depths of about 800 feet, thanks to a system of internal and external ballast tanks.
We have 5 external ballast tanks that are normally filled with air when I'm riding on the surface. When it is time for us to dive, we'll open vents on those ballast tanks. There's grates on the bottom of the ship that allow water to...
Already, you should be able to answer question 1. What are the tanks on the ship side of a submarine called? Oh, MrStav, I missed it. It is ballast tanks. Okay? So what they're showing you on their submarine, there's a ballast tank that is here and a ballast tank here. Depends on the submarine. Some submarines actually will have a ballast tank along the side, like a swim wing. You know, like kids wear those like, and then they go swimming. Okay, so they have those are essentially like ballast tanks on the kids' arms. So submarines have ballast tanks, and so in this submarine, they have one at the front and the back.
We have 5 external ballast tanks that are normally filled with air when I'm riding on the surface.
Okay, so these ballast tanks are filled with air when they're at the surface.
When it is time for us to dive, we'll open vents on those ballast tanks. There's grates on the bottom of the ship that allow water to come in, displace the air, making the ship...
Okay, so those ballast tanks are filled with air when it's floating on the surface. But when the captain says, all right, down we go, okay, all they do is open up the vents at the bottom. Okay, so this guy has the ballast tank right in the middle. Okay, that's what I was filling with our soda, our powder, our baking powder. Okay, so the submarine opens those ballast tanks and they quickly swamp with water, right? And that makes it so heavy that they sink.
Just slightly negatively buoyant. We then proceed...
So what he says, just slightly negatively buoyant. So they're calculating how much buoyancy is pushing against them. Okay? And then they are letting enough water in, so they're just beating that buoyancy. If they like way exceeded the buoyancy, then the submarine would do this. Okay? So let's go back to these bad boys. Okay. This pipe was way exceeded the buoyancy force, and so it just dropped. Okay. As opposed to my guitar pick, which slowly fluttered to the ground. Okay, because these are just past the buoyancy point. Okay, compared to this one where it just sinks. Wow. So why did I use these test tubes? Because these test tubes are like the ballast tanks on a submarine. When they want to float, they cap it, and they sit on the surface of the water. But as soon as they open up the cap, they fill with water, and down they go. But now you see how fast that sunk? So a captain has the ability to calculate and just let enough water so that they don't like just sink like a rock. They just go down in a nice controlled manner, and then they level out by closing that cap and not letting more water in. There we go.
To the depth that we want to go to. And we use internal ballast tanks to make the ship neutrally buoyant, but then we can...
Neutrally buoyant. Okay? So they're sitting on top of the water. Okay? So the buoyancy force is greater. Then they let water in so that they're under the buoyancy force, so that they go underwater. And once they're underwater, then they level it up the ballast tanks so they're neutrally buoyant. So now that they're not less than buoyancy, otherwise they go back up. And they're not greater than buoyancy, then they would sink. So they're able to stay right in the middle. Sick. There's a lot of science to these submarine thingies.
That's on our way, whatever depth we choose.
The crew on board the Virginia class have an abundance of cutting-edge controls at their fingertips, one of which is replacing the most iconic feature in submarine history. The periscope has been a key component on the submarine for over 100 years, but engineers on the Virginia class are taking a bold step toward the future by replacing the periscope with a state-of-the-art photonic mast.
The photonic system is a mast with a sophisticated camera system that allows what would normally be displayed just in a periscope to be displayed on widescreen monitors throughout the ship.
And it used to have an optical periscope that came down, which drove the construction of the submarine and the orientation of all of the rooms on the submarine.
Bulky periscopes force most submarine control rooms to be located on a cramped upper deck. On the Virginia class, the compact imaging equipment is housed in a part of the submarine known as the sail. This allows the sub's control room to be built on the wider second deck.
My control room that I'm standing in right now houses all of the important decision makers. It really brings the crew together to operate as a team, as a unit.
Okay, so you're looking at these words, positively buoyant, negatively buoyant, and neutrally buoyant. Okay, they were talking about the periscope and how their submarine can be comfortable, but what we're worried about is they fill the tanks with air to be positively buoyant, okay? And then they let water in, so they go underwater, so they're negatively buoyant. And then they level that out so that they can be neutrally buoyant and stay underwater. Okay? So looking. Oh, where's the mouse? There we go. Talking here. When they're at the surface of the water, they are positively buoyant. So that means the buoyancy force is greater than the gravity force. Okay, then they let the water into the ballast tanks so that they are negatively buoyant, so they are greater than the buoyancy force. The gravity is greater. And then when they're ready to travel at mid, they become neutrally buoyant, so that the force of gravity is equal to the force of buoyancy. Okay? So neutrally buoyant is when they're equal and they're able to stay in the middle of the water. Okay, negative is when they're sinking, and positive is when they're at the top of the water. Now, if you're asking me, Mr. Staff, well, how did I make this thing float and sink? Can't tell you my secrets. Let's watch the next video. This is the last video, folks. I apologize if you're bored, and if you're bored, it is Brooke's fault. This, my friends, is a fish. Hello, fishy. All right. Now, last time, somebody in the chat wrote that Miss Boys would be cringing at my artwork, and I'm offended by that. Whether it's right or not, I'm still offended. So here's our little fish. Now, this is a high-quality video. I think you're going to enjoy it.
Hello, this is Scott Fish, and I'm going to talk about swim bladders. So all fish have swim bladders, and
So, this is made by a kid, but it's very well done, and it explains swim bladders and fish very, very well. So we are on to this slide of your unit binder, swim bladders. How do they work? Okay. So what this child just said is that all fish have swim bladders. So looking at the organs inside of a fish, this is a bladder. And essentially, we could call this the ballast tank. The ballast tank of a fish. Okay? So what is a swim bladder? There we go.
Swim bladder is an organ in a fish's body that can expand and contract.
Yeah, that's very important. It can expand. Why would it expand? Why would it contract?
It's by either adding or taking away gas from the organ, and if the fish adds gas to the swim bladder, then he will float more towards the surface of the water. If he decreases the gas in the swim bladder, then he will become heavier and sink in the
Notice that the fish is now upside down because it is sank to the bottom.
water column. This is the same way that submarines work to move up and down through the.
And notice the stages. The top fish has the biggest swim bladder. So what do you think it's full of? Let me know in the chat. What do you think that swim bladder is full of? Okay, that's the one at the top of the water. Okay, compared to the fish that is at the bottom of the water, has pretty much completely deflated swim bladder, completely flat. Okay, yeah, air. Okay, that swim bladder opens up and it fills with gas, with air. Okay, and that's what makes it float, just like a ballast tank. Okay, it makes positively, make it positively buoyant.
Column. Now I'm going to talk about swim bladder disorder. The more common swim bladder disorder is when the fish ingest air while they eat. This is more likely to happen in fancy goldfish than any other fish. So sinking food is really good for goldfish.
Okay, so we're talking about swim bladder disorder here is that some food floats on the top of a fish tank, and so the fish have to go up, swim up to the top of the water, and then kind of poke at it and get it out. One of the problems is when they go and they open up and they take in that food, they're also taking in gas or air, and they're filling their swim bladder.
With this type of swim bladder disorder, the fish is not able to swim down or flips on its back at the surface of the water.
Why do you think that? Why would they not be able to swim down? Okay, it's because that swim bladder has filled with too much air. Right now, it's acting like a life jacket inside of its chest. Right? Ever tried to swim down with a life jacket on, and it just like swim. Okay, it's very frustrating. And imagine being a fish, and that is your way of living, is being underwater.
And it actually has nothing to do with the swim bladder. It's just that the air that they ingested while they were eating is stuck in their intestines, so they can't control their buoyancy.
Okay, so what she said is not have to do with the swim bladder, because when they're digesting that water from the top of the surface, that air is going in, but it's not going into its swim bladder. Because the swim bladder, it has control of. It can squeeze its swim bladder and get all the air out. But when that air goes into its digestive system, it can't squeeze those organs to release the air. Okay, so fish bringing oxygen into their swim bladders is a good thing because they can control that, open and close it to go up and down. But when air gets into their digestive system, that is a problem for the fish. That is a problem. Okay, they can no longer go down because it's like a life jacket in their intestines, their digestive system.
For a true swim bladder disorder that is actually harming the swim bladder, it is not normally curable. Some people have made contraptions to help the fish stay afloat because they can't expand their swim bladder anymore. But unfortunately, this real swim bladder disorder is not from fish ingesting air, so it's not easily cured, and it normally causes death of the fish. So I hope that you all enjoyed this little video about swim bladders and fish. So thanks for watching. Please like, subscribe, and let me know what videos you'd like to see. Bye.
So there it is. You see the videos aren't very long. Okay, what is a swim bladder disorder is the question. Okay, and that's it for buoyancy. That's the lesson. Okay, so we covered a bunch, introduced you to a bunch, and we had some fun sinking stuff and floating stuff. And with that, I will leave you with my magic submarine. Here he goes. Yeah, buddy. Buoyancy, folks. The buoyant force has to overcome the gravity force. And I'll just keep watching this so the chat can stay open for a little bit. You can ask me some questions. And this is so fun. Thanks for watching. You guys have a good one. Good luck. See you at Guided. Peace out. Peace.